Physical World, Chapter 1, Section 2, Digging Deeper, Measuring the Motion of Lithospheric Plates. Types of Crust. In the Investigate, you gathered scientific information about the North American plate from the This Dynamic Planet map. You collected evidence that Earth's moving plates can carry parts of continents as well as parts of oceans. You then analyzed GPS data and used this as evidence to explain the movement of the lithospheric plate on which the United States is located. Geologists, or types of geoscientists who study the materials, processes, and history of Earth, divide Earth into layers by chemical composition. The layers are the core, the mantle, and the crust, as shown in Figure 1. Geologists base this division on several kinds of evidence. You will learn more about the evidence in later sections. You will also learn about the chemical structure of each layer. The crust is the thin, solid outermost layer of Earth. The crust is divided into oceanic and continental crust. The crust beneath the oceans, and the crust. I want to keep this diagram in view. Okay. The crust is the thin, solid, outermost layer of Earth. The crust is divided into oceanic and continental crust. The crust beneath the oceans and the crust that makes up the continents. The oceanic crust is younger than and not as thick as the continental crust. Beneath Earth's crust is the mantle. The boundary between the crust and the mantle is well defined. There is a change in the chemical composition of the rocks. The rocks of the mantle are not the same as those of the crust. Most of the Earth's mass is contained in the mantle. Below the mantle is the core. It is the innermost and hottest part of Earth. Earth's interior can also be divided into layers based on physical properties. As you move from the crust to the interior of the Earth, there is an increase in the temperature, pressure, and density of the materials. You will learn more about density in a later section. Let me scroll back up so we can see this diagram as I'm talking about it. The topmost part of the mantle is cooler than the parts below. This uppermost part of the mantle moves as a rigid block, carrying the crust with it. Remember that this top part of the mantle, together with the crust, is called the lithosphere. Lower down in the mantle, it is hot enough so that the mantle material can flow very slowly, just like a very thick liquid. This part of the mantle is called the asthenosphere. Below the mantle lies the outer core, which is liquid. The innermost and hottest part of Earth is the inner core, which is primarily solid. Continental crust forms Earth's continents. It is generally 30 to 50 kilometers thick, and most of it is very old. Some continental crust has been dated as 4 billion years old. The geologic structure of the continental crust is generally very complicated, as you will learn later. In contrast, the oceanic crust is only 5 to 10 kilometers thick, and it is young in terms of geologic time. All of the oceanic crust on Earth is younger than about 200 million years old. So let me go back to these two diagrams. This is a diagram showing the layered structure of Earth's interior, where you have the crust, the mantle, the outer core, and the inner core. This diagram shows the layered structure of the upper mantle. You have oceanic crust, continental crust. You have a rigid lithosphere. You have your upper mantle and your asthenosphere. Okay. This is a cross section through the outer part of Earth. Measuring plate motions with GPS. The Global Positioning System, or GPS, consists of 24 satellites. These satellites orbit Earth at a height of 20,200 kilometers. Receivers at stations on Earth use the signals from satellites to calculate the location of the station. An example of a station is WES2 in Westport, Massachusetts. Geologists have set up a network of targets all over the world. They use the targets in order to monitor the movement of lithospheric plates. Steel spikes pounded into the ground make up the targets. The spikes are located in solid rock. A high-precision GPS receiver is then mounted on a tripod. It is positioned directly above the target as shown in Figure 4. The targets are revisited over a period of months or years. The receiver measures the distance to 4 or more GPS satellites. The receiver then uses stored data on satellite locations to compute the location of the target. Changes in horizontal and vertical positions can be detected within several millimeters. Figure 4. A GPS receiver is used to measure changes in elevation of this volcano. GPS data collected at stations all over the world confirm that the surface of Earth is moving. However, GPS time series data do not go back very far. GPS is a new technology, and a global network of GPS stations has only existed since 1993. How do scientists know that the surface of Earth has been moving for a longer period of time? The answer to this question comes from the study of rocks.